Hee. Hi everyone. You're gonna notice something a little different this evening. Couple things. One, I can't lift my hands. My sensor died, so I have to wait. I have a new one coming in the mail. I'm hoping I'll have it before next Wednesday, but yeah, this proto is gonna just have, my floppy ears and fun faces. But in the meantime, no hands, which drives me a little nuts because I talk with my hands. So that's the first thing. Second thing, we have a better camera on the bench for seeing stuff and things. Which let me. I want. Yeah, that one. Nope. Yep. Hang on. Nope. There we go. So something that was driving me a little nuts is that there was no mechanism for you guys to see in the electronics up close because it was just simply too blurry. So with that, I can now zoom in and out with some hella nice detail. So yeah, we got that now. I would like to thank you all, with your bits and donations towards this channel, partially helped fund that camera. So I would like to say thank you. That helps this, helps me bring better content to you guys. So I very much appreciate that. Thank you. Oh, we got a Firefox a little. Hello. I would wave to you, but I can't move my hands. That's gonna drive me nuts. The sensor died, but it's okay. We're not gonna dwell on it. Tonight, what we're gonna do is we are going to wrap up day 15 of the 30 Days Lost in Space series. I kind of left it on a bit of a cliffhanger after, I don't remember, it was either 5 or 6 hours of me tinkering with the code, that I came to the conclusion that I probably should stop. Offline, I did take some time to look at my code after taking a break. I think it was a day or two later I looked at it. I fired it up to figure out what I was missing. So I now have it working the way I wanted it to. I'm going to showcase that briefly, and then we're going to get into the day 16 content, which we're going to get to play with I think it's an 8-segment display. So we're going to play with screens and make them blink and show things and numbers. And I think there's a colon on this display, the symbol of the colon, like you would have in time. But nor here nor there. So by all means, let's get into it. Haha. Okay. So, from the last time of the 30 Days Lost in Space, we were working on making ourselves a keypad. Actually, here, let me demonstrate from over here, because I actually would like to get this in frame. Scoot my stuff over here a little bit so I can bring these where we can see nicely. So, briefly, where we were at with 30 Days Lost in Space is we had the big red button, right? And if I hit the big red button, it locks out the keypad, right? Because we were talking about computer access. And the one thing I wanted the code to do, there was 2 things in the creative day that I wanted our stuff to do that required some research during the stream. One was for the pin to unlock the system that we put in on the keypad here, to remember the 4-digit pin that we set in the code. Because if you remember, when power was lost, the system would forget the 4-digit code to unlock itself. So by losing power, it would reset it to 4 zeros. That's not useful to us. If the power disappears, we want it to hold that information. So we figured out how to store our 4-digit number in memory, and I will show you that in the code again. The thing I couldn't figure out initially is, or near the end of stream, was if something happened to the memory in over here, if another piece of code accidentally overwrote one of our 4-digit pin options to something that wasn't mapped to our lovely keypad, well, then I wanted the board to know that and factory reset itself, essentially, and set it back to 4 zeros if any of those keys were not clickable. Because if for some point, if it was a safety guard, because if in some point in your code you wrote something that overrode that memory address, or if something buffer overflowed and it wrote to that memory address and you didn't intend it, it was a mistake, well then it potentially put a character in there that was not on one of these 16 keys, which then there would be no correct combination to unlock the system. So this was just simply a safeguard I wanted to put into place to prevent accidental permanent lockout without the need of rewriting the code on the board to basically reset it. Because now that it stores the pin in a memory for this access control system example, if we accidentally overwrite the memory address with something that we can't click, well then now we're screwed. We can't get in. So I wanted that mechanism to be built in there, and it was something with the looping logic. I don't know, I'll show you. But now here's where we're going to try my memory. I don't remember what I set the pin to on this, and I do know that this also does remember the last pin I set. So we're going to try to access the system and see if I remember it. I'm going to toy with the lights here a little bit though. So I'm curious to see how well this LED is going to look in here. So we're going to zoom us in on our board here. So we have our red LED right here and our green one right next to it. And if I hit the big red button, it locks out the system by briefly lighting up both LEDs, 5-second timeout, and then it resets itself, waiting for the star to enter a new password or pound to enter the system. So what we're going to do is we're going to try to unlock it and see if I remember what I set it to. I'm going to click pound. At least I think I'm going to click pound. Enter pin to continue. Oh, interesting. I think I accidentally unplugged something. Access denied. Cannot change pin without current. So let me scroll up in the code here and see what the current, or what the pound symbol was. I think I clicked on the wrong section here. Let's go back up to the keyboard. Oh, pound was this one. Okay, so pound is here. And then I thought I set it to 1, 2, 3, letter A. Interestingly enough, that one's not. Oh, the wire's not in the whole way. Aha! The wire was loose. Yeah, there's no way I'm going to get in if not all the wires are connected. And just like that, on the screen it now says that I'm authorized, but more importantly, our LED turned green. And I can lock out the system gracefully by hitting the big red button. So now let me show you what that looks like in the code to give you a better idea of what we ended up doing. All right, and as a matter of fact, I think I am gonna turn the lights back on here. Actually, yeah, I'll leave them on. Oh, that's right, I forgot. My VTuber follows me now when I get up, but you guys can't see because I'm on a different scene. That's the scene I need. Haha, hello. It's not like I haven't done this several times and I still screw up here. What do we got here? Michael! I'm here to sell toaster and toaster accessories. Hydrate! How dare! Of course, I have my tea. What do you have, Michael? Do you have water, tea, soda? A case of ice that you're just kind of chewing on? I mean, there's lots of options here. Let's see here. Huzzah! All right, there we go. Ooh, root beer. That's solid. No, that's fair. Yeah, I'm not surprised. Does Nadia regularly like to knock over drinks in like a cat, even though she's not a cat? Because I feel like that's something that Nadia would probably do. You're probably a firm investor into paper towels at this point if she meanders around the way I think she does. For those of you in chat who don't know Nadia, she's a ferret, and she likes also clicking Michael's keyboard when he's not paying attention. She likes to snuggle up with the keyboard. I mean, which is fair. Most laptops have very warm keyboards. Oh, interesting. So she is not a fan of knocking them over. All right, fair. All right, cool beans. All right, yeah, so to complete my thought on day 15, that's where we left off. I have nothing additional I'm adding to this. I just want to show you what I did to make this work the way I wanted it to. So let's see here. Oh, hello, thank you for the follow. I am terrible at saying names. Oh, good God, help me. Quick, in chat, tell me how to say your name, please. I'm in danger. I saw Vim on the end, kind of like the editor in Linux, but I'm sure you probably don't want to go by that. By all means, tell me how you would like me to refer to you. Also, hello, welcome in. Let me see here. Yeah, so those were expected. This I didn't have to change, so this is where we then chose our 3 memory addresses, because we were storing 4 different values, 0 through 3, because everything indexes at 0, because of programming logic. Gotta love it. He removed a lid for ice water. That's awesome. Nadia is very skilled in the abilities of getting into things, which is very acceptable. Let's see here. So then we're storing excuse me, char characters. So we then select those, which we did do. Nah, that's for Michael. Let me see here. Okay, so I'm gonna be honest, I don't fully remember what things I changed and what I didn't, but I'm just gonna cover the logic that I had ended up getting that works here. So we have a variable that is an array variable. Give me a moment, I actually switch up the audio here. I meant to switch it to the lo-fi. I forgot to do that. There we go. Toaster terms. I see what you're doing. Yeah, so I made a Boolean array variable, valid options check, and it holds a total of 4 Boolean values, which that is every click of our password, because there's 4 digits. Now, if the pin length was variable, right, well then right here we set it based on the pin length that we have set up top, which is a total of 4 digits. And then we initially set them all to false. So if we can't read what's in memory, then one of those 4 digits will return false, right? And this is where we're storing the results. And then let's see here. We have to scroll down a little bit to find what's the meat and potatoes of this example. EEPROM.get is what allows us to read out of memory what we stored in the memory address that we set. So think of the flash drive that you carry around with you and you store your Word documents, your pictures, your music, you know, your cute Protogen pictures, whatever, right? And normally you just type in the name of the thing that you saved in search and you could find it, right? But what we're doing here is we're telling it that we want to get out what is in memory address is 0, because that's where I stored the first digit of our PIN, and storing it into an array, right, of password that's a total of 4 in length, which I did clear up above. I scrolled past it. So we go to the first memory address, which is 0, and store it into password 0. That's the first position in the password variable. And then we do the same thing for the rest. So address 1, password 1, address 2, password 2, address 3, password 3. That then pulls out what was written to those 4 memory addresses and stores them into a variable that we can actually look at. Now this next part is incredibly important. We have a total of 16 valid options on our keypad that we can click in the physical world. if one of the things that we stored in this one of these 4 memory addresses is not one of these items that we see here on the screen. So that's 0 through 9, A through D, and then the pound symbol and the star symbol. If for some reason we have something other than these 16 different digits, then we need to reset it, because there would be no way into the system then at that point. So this is where I ran into some trouble. I kind of had an idea of what I wanted to do here, but let's walk through it. This is 2 separate loops, because we need to check a total of 16 things against, because there's 16 options, against every single digit of the pin, which is 4 in length. So we have to take 16 times 4. That's how many times we have to check, right? So the first loop is just to simply say that for each iteration of the password, right? So the outer loop, which is this first one, runs 4 times because the pin length is 4. And then the inner loop that runs inside of the outer loop runs 16 times because there's 16 options. That allows us to check each individual character of the password and make sure that it at some point matches one of the valid options we can click on our keypad. So then we go into an if statement. It says if the valid option J, which is just the position of our inner loop, because each time it iterates, it's going to start at 0 and then it's going to increment by 1 until we hit 16. 16 is not less than 16, so then we break out. If its a valid option is equal to, that's what the double equal symbol is a comparative operator, which means we're comparing to something, not setting it equal to something. This says, is the thing on the left the same as the thing on the right? It does not set it. It's just looking at it. It's comparing it, which is why it's called it's got a comparative operator. And then position I, which is the outer loop, because there's only going to be 4 combinations of the password we need to check against. 0 through 3. If it so happens to be true, oh, I clicked there. Best password ever, I, right? Oh no, oh no. No, that's the positional point. That's where we're looking in the loop. So it's 0 through 3 on the available options. I realize that's a little confusing. Apologies. If it is equal to something in our list, then we say that for one of the 4 options is set to true. That means that is an option we can click on the keypad. That does not show anything in the terminal. It just simply stores it back into the variable that we have up here. So that makes this first position equal to true. And then we loop through the other 4 passwords and check it against all 16 available options. If at some point, actually, so yeah, that's right. That was the other part that made this a little convoluted. And that was if it was set equal to true and it reached one of these options, I needed it to stop. I didn't want it to keep checking, because if it kept checking, it could only ever be true. It could only match one of these items because it's a single digit in a password. So once it hit something that I was able to click, I needed it to stop and then start the next iteration of the loop, the outer loop. So we start at loop 0. We run through this 16 times. And then once we hit one of the options that are correct, that I can click, I need to stop. That's what the break command is for right here. This break says that I hit an option that was true. This else statement now can't run. And since I broke out of the loop, that breaks this inner loop. So the rest of the 16 options that it's going to check, it doesn't do. And then it goes back to the outer loop, which is this outer portion, and then checks the other 3 positions of the password from within memory. As long as everything checks out and nothing is false, which would mean what was read from memory does not match what's in this list, we then check the, let me see here, where is that? Memory pin. I'm stopping here because I have to read it. All right, so we have another Boolean function that is the either going to be true or false, because it's either going to be yes or no. And then we then call the function that I wrote that is called isStoredPinValid. So now that we've ran through all the options, we then call on the function that is called isStoredValidPin, which I think I got to scroll to the bottom for that. Yeah, here it is. So then what we do down here is, now that we've filled out filled out all 4 positions of the valid options check from the loop at the top, now down here we check to see if any of those 4 positions are false. As long as none of them are false, that means that it's true. That means all of the options that we have in memory match a physical button we can click. So then we return true. Otherwise, if one of those 4 positions 0, 1, 2, or 3 are false, we return false. Because if any of the positions of the password, whether it's position 0, 2, 3, are not clickable, well then we need to reset it, because there's no way for us to type it, which would keep us locked out. So we read what from memory, and the pin I typed in there was 1, 2, 3 letter A, and that let me into the system because that's what it read from memory. Those are all valid options. So this, when the code started up, returned true. Now it runs back to the top because a function can be called and the code picks up right from where it left off. That allows the compiler to jump through the code a little bit here, which is going to require me to go find my place. So then the memory pin would be set equal to true. So we took 4 trues and combined it into 1. So as long as it was true, there's nothing more we need to do, and we would continue with the rest of the example as we were. If one of those positions was false, that's when this if statement right here takes over and does a couple things. It sets all 4 positions of the password to 0. And that's in the running memory. The password, the variable called password that is used in the code lower, is all zeros. Now, this part right here does not change what's written in memory. The stuff below it does. So right here, the put command allows us to write to memory, so when the board loses power, what's in it. So this right here is actually setting all 4 memory addresses to the digit 0. And then it tells the user, hey, there was an issue, I reset your pin to all zeros. So that the user now knows that there was a problem with reading the memory, and the code saved them, so now they can actually click the buttons on their keys. And then from there, the code goes into its primary loop, and then it's exactly what we saw last week. You can click the big red button, which right there calls out the lockout function, which then causes those LEDs to blink. It pauses the code for 5 seconds. It just pauses the execution, by the way. That's literally all it does. It just stops the code from moving. That's how it locks it out. It just doesn't allow it to proceed. And then it writes out to the terminal that I have down here behind my head. Let me move myself out of the way here a little bit. It calls system panic. It locks it out, and then after the timeout, it goes back to the primary code saying, use an option. And that is the wrap up from day 15. Where I got stuck was in this loop. Oh, scroll too far again. This section right here is where I got stuck, because I was having trouble figuring out the right way to figure out if it was a valid option, and then to proceed to check everything else. By causing the code to stop with the break command, in fixing a little bit of my logic that I had here. I had a little bit of this goofed up. That then permitted me to get the solution I was looking for. So there is no shame in taking time and stopping, taking a break, and then picking back up where you left off with a fresh mind, which is exactly what I did. Anytime you spend time looking at code, whether it's an example that you're following out of a book, a tutorial looking at online, maybe you're going to try to redo some of what I'm doing here, because I show the code on screen, I walk through it. If you get stuck, there's nothing wrong with taking a break. I do it all the time. Because it really boils down to the fact that sometimes you're just no longer in the right headspace to work on this kind of stuff. And that's okay. That's 100% going to happen working in this field with any of this kind of stuff, whether it's in a hobby land or if this is your daily job where you work with this kind of stuff. And with that, we're going to proceed forward, because now that we've wrapped that up, now I feel like we can actually dig into day 16, which I'm really looking forward to. We get to play with I think it's an 8-digit segment display. I don't know, we'll see here in the example. But yeah, so I'm going to just let the video play and then we'll work on getting the wiring set up. So yeah, let's jump into that.
A new week dawns, my courageous counterpart, and it brings a fresh set of challenges to our undersea sojourn. You may have been enjoying the soothing serenity of the deep ocean, but it's time to point our sights towards the surface. Now, don't get too excited. We can't just jet up there like a dolphin on an energy drink. There are imperative protocols to be followed. As any experienced explorer, such as yourself, knows, rising to the surface too quickly will reduce pressure that will cause our spaceship to explode like a shaken soda bottle.
That would be bad.
And I believe neither of us would be particularly fond of that outcome.
That's fair.
First things first, power. We need all we can muster. So, it would be best to attempt our surface-bound journey when power generation is at its peak. That means midday. To do that, however, we need to know when exactly that is. In other words, we need to build a clock. There's also the matter of the encrypted source code provided to us. Decrypting it is crucial for all of our plans to unfold. So, we have our work cut out for us this week. We need to create a clock, decrypt the code, and most importantly, limit the rate of ascent to prevent us from becoming a bursting submarine balloon. Now, let's put our crafting cap on and get down to business. We've got a spaceship to guide home. Right then, let's dive into the fascinating world of timekeeping. To craft our clock, we'll be making good use of a charming little component in our kit, the 7-segment display.
Oh, it's 7 segments.
Intrigued?
Okay, I was close.
Allow me to explain. A 7-segment display looks like this. It contains a total of 7 LEDs, A through G, in an 8 formation. Each of these LEDs can be individually illuminated to make numbers and other characters. Simple, yet ingenious. Let's imagine a digit.
Maybe,
How about
Michael.
an 8?
Maybe.
Notice how it's essentially a formation of different horizontal and vertical segments? Now, think about how you can form other numbers by lighting up or turning off different combinations of these segments. If we turn off the horizontal segment in the center, for example, we turn our 8 into a 0. Behold, the power of a 7-segment display. Simple, yet incredibly useful. It's not my intention to befuddle you, dear explorer, but the digits aren't the only things a 7-segment display can render. With a bit of creativity, you can also display a few letters and symbols, but we'll save those for later. For now, find security in understanding the basic concept of a 7-segment display and prepare to harness the power of this nifty little device to create our clock. Ready for a bit of digital wizardry, explorer? All right, Explorer, buckle up as we dive into the wiring part of our adventure today.
Hey, Pyro.
You'll be relieved to
Welcome
know
on in.
it's quite straightforward with just 4 wires needed for our 7-segment display module. Here's how we do it. As always, we connect the ground wire here and positive here. These are our data pins and need to go here on our digital pins. Our friend CLK stands for clock pin. Its job is to compile the binary data streaming from the DIO pin into a byte. 1 cycle equals 1 byte. Our other friend, DIO, stands for digital input-output. Its role is to receive binary data for the hero board, which in turn determines which segments of our display are going to be dazzling us with their lights and which ones will remain in the dark. Think of it like a switchboard operator of the olden days, but for data bits. Now, an 8-bit binary number provides just enough digits to control all these segments and even gives us a few to spare. So, there you have it. Simple, isn't it? The magic of making numbers out of light is within our grasp. So let's press on, shall we? Now, Explorer, we're going to make a bit of a shift from our hardware chat and delve into the coding realm for the day. Here's where we bring in our secret weapon. A brand new library. Rest assured, Explorer, I'm happy to provide you with a refresher on library installation. Here's how it goes. Navigate to the Sketch tab in the top menu. Then move to Include Library and click on Add.zip Library. This way, we'll get all the resources we need without having to invent the wheel all over again. It's quite handy, isn't it? Do be sure to add the library to the top of our code so we can utilize it. Now, by creating this new object, we'll be granted access to the entire library of the new 7-segment functions. Remember, you must not forget to define those pins. The one we'll be most interested in is the Set Segments function. This function is like the puppet master behind our 7-segment display. Allow me to break it down for you. Each of the 7 segments of our display, labeled A through G, can be controlled individually and can combine to form different characters. Each segment can either be turned on, meaning it lights up, or off, where it remains dark. The Set Segments function helps us control which segments light up and which do not. It's essentially taking the reins and directing our display to show specific characters. How does it know what to display, you ask? It takes an array of segment states as an argument. Each bit in the array corresponds to a specific segment. When a bit is 1, the corresponding segment lights up. When it's 0, the segment remains off. In essence, Set Segments helps us paint pictures, or rather numbers and letters, on our 7-segment display by controlling the light show for each segment. It's pretty cool, isn't it? You see, each segment labeled from A to G represents a different LED that we can command to light up or remain off. With this in mind, let's dive into some examples. First up, think of which LEDs we'd need to ignite to display the number 7. If A, B, and C came to mind, then I'd say you're getting the hang of this. What do you say we step it up a notch? Think of which LEDs we'd need to light up to spell out the letter A. Whew! I can see those gears turning. By my calculations, it appears you're thinking A, B, C, E, F, and G. Well, dear Explorer, that would be correct. Now, for our final round, let's challenge ourselves a bit. Can you figure out which LEDs we'd need to illuminate to spell out the word done? This is a bit trickier, but I know you've got this. Remember, practice makes perfect. Keep playing around with combinations and soon you'll master the art of the 7-segment display. It seems to be that time where we turn to some instructional material that I have gathered cached on the computer. I've also added this to your mission resources for future reference. Good luck.
That'll be fine.
All right, welcome back to day.
Hello. Ah. Okay. Alright, so there's our wiring diagram, and as promised, we've got a total of 5 wires involved. Oh, excuse me. Interestingly enough, no breadboard this time. These are all direct connections. So first things first, we still need to mop up what we've done from last week. So to prepare for that, I need to wipe the code that's on the board off of the board. So this is where we're going to get our library for the 7-segment display. We'll have to install that. But before I do that, we're going to do a new project. Just kind of hoping that would steal the name. Okay, and before I do anything else, I need to clear the code that's on the board. So right now, if we take a look at the terminal, and I hit my, actually there you go right there. That's what it does on startup now, which actually here, before I completely wipe the board, let me just hit the reset so you can actually see that. And I can even hit the big red button. There's our system panic. But now I'm going to upload this empty sketch. So if I show you, you're going to see here that red light's going to go out when I hit the upload button. And now that I've uploaded a blank sketch to it, we'll now see that if I hit the big red button, I clicked it, nothing, because I've reset it. So what I have done is I have erased what was the storage for the project, but there's something that I didn't do, and that was erase the values in the memory addresses 0 through 3. I'll be honest with you, I don't know how to clear those just yet. I know that there is the put command that I can use that allows me to change what's in there. But I don't know how to write nothing back to those. I'm wondering if maybe I could call on the put library and just pass it empty quotation marks to clear the memory. I don't know, we're going to dig into the display, and then that's probably going to either be addressed on another day or maybe later. I don't know, we'll see what time looks like here. So right now the board has now been reset, and now we can work on the wiring up of the new display. I'll back us out here a little bit. Yeah, Pyro. You are correct. It is a new camera. And it's one that lets us better see what on earth I'm doing over here. So before I disconnect anything else, I'm going to disconnect the hero board from the terminal. And then I can disconnect the keypad. Disconnect our big honking button. And then I'll grab some bags here for those components to put them away so I don't lose them. We've got both of our LEDs. And then our 220 ohm resistors. Those away. And then we have the, I forget which one this one was. Yeah, it's like a 1000 ohm, I think. We'll get that out of there. That's our pull down resistor to make sure that the Arduino can understand the different readings that it would get off of those other things.
And then we've got our little buzzer. And then I can disconnect the rest of these because we don't need them for the new example. Yeah. So it takes that out of the equation. And these as well. Always feels a little sad to disconnect something that you got working. It's okay though, it's a part of the learning process. Alrighty, and then we're going to need a total of two of the male to female connectors, which I think, if I look at this, yeah, I guess I could just get them off of here, which is totally fine. It's not gonna bother anything. And then without further ado, we have got our display. And there's our headers. And chips on the back. Yeah, and it's even labeled. You can even see the writing on there for what the different pins are for. If I can get that in view. Yeah, clock, ground, VCC. So that's what we're gonna hook up to our friend that's over here. Which, oh, that's correct. I actually need 4 of these, not 2, because 2 of those are gonna get plugged into the other side. We have that right there, and then there we go. Okay, now I have everything I need. All right, so I'm gonna pull up the example here. I can see where the heck I'm plugging stuff in. Okay, so first things first, we're gonna hook up our power and ground, which, looking at this, it orients it this way with the pins to the right, which means I'm going to do the same. And I get to push those on without much of a worry of much of anything. That's where those 2 are going to go. And then the bottom one is my ground, which is the darker gray. And then the white is my 5 volts. So that's 1, 2, 3, 4 from the bottom. 1, 2, 3, 4 from the bottom. So that gets those 2 hooked up. There we go. That gets those hooked up, and then we get to do our data and our clock pins, which are going to be the other 2 here. So these 2, I'm going to push on like that. The top one is clock, which in this case is purple for me, and that goes into 6. Which is a PWM port. And then we've also got 5 directly below it. That is our, which pin, which did it say? The DIO, which is the one that actually accepts and receives, or it accepts the different things we send to the display. So now, I don't know what's going to happen on startup. I've erased the code from the board, so other than our pin from our previous example I stored in memory, there's nothing else on here. So I think what's going to happen is that the 5 volts is going to hit this. I'm thinking we might get a flash on here, but I would think it should then shut off. I guess it really depends on what this chip on the back of the display does with no instruction set. So let's find out. Interesting. So nothing is the answer to the question on what happens when you initially power this on. Interesting. All right, well, I'm gonna get us nice in frame here. We can get a good look at that. There's nothing we really need to see on the actual Hero board itself, so I'm gonna just keep that nice in the middle of the frame, because as far as the wiring goes, that's everything we need for there. I did not forget about Twitter, I just didn't do it. I did put it on Blue Sky though, which I actually do have to add to my socials on this platform. Okay, so now that we got that action out of the way, we're now gonna go get the library. So the library is just pre-written code that we're just going to take advantage of so that we don't have to, as she in the example had noted, reinvent the wheel. It permits us to take advantage of existing libraries and save us some time and some code. So we're going to go grab that. And then we need the 7-segment display library. I'm gonna save that. Okay, so now that we have that, we can go to our library section. Which actually I think I might do it from here. Yeah, include library, add zip, which I put in downloads, and just grab it right from there. Okay, it successfully installed the library from the archive we provided to it. So I can close that out, and now that we have the library, we're then now going to be able to call it. If you forgot that step during this process, it's fine, nothing bad would happen, it's just the code won't compile. It'll try to call on a library that it wouldn't have installed, and then it wouldn't know what to do, because it's relying on code that's not available to it. But thankfully we have it. So now we have that. Well, let's see what we're dealing with here. I'm actually kind of curious to see how much stuff is actually here. Alright, so it's not a lot of code, but let's dig into it and see what we can find here. Alright, so it says sound and light gives us some good feedback from our hero, but what about when we need numbers, then the serial console isn't available, like as if the board wasn't hooked up to something. That's actually a valid question. Today we introduce a 4-digit 7-segment display, the TM1637. This is mostly for numbers, like a counter or perhaps a clock display, but with some imagination we can also show some characters. Which does make sense, because some characters overlap with what some numbers look like, which kind of makes sense. Alright, so let's see here. So it says, Arduino concepts introduce documentation in this lesson. Is binary notation and the idea of logical OR. Okay. Okay, so like in any project, we need to include the library for the Arduino, which is the hardware that makes the Arduino function. Every single project that we have is going to contain that line of code. Because if we don't have that line of code, then we can't interact with the hardware I have plugged into the computer. Very important. Alright, so it says, please refer to the lesson and lesson videos for instructions on how to load the library, which we just did.
for the first time, which we now have. Now that we've installed the library, now we need to load it, which is very similar to loading the include for the Arduino, except we just call on the name of the library that we installed. Obviously this name is specific to the name of the library, so you have to get this spelling correct or it won't work. Okay, so even though there are 4 pins to our display, one of them is ground and one of them is just the straight voltage to the display. Neither of those are controlled pins, they're just static ones. So our actual pins we're going to interact with are pins 5 and 6, which is what we're going to declare here. The clock pin was number 6, and then the DIO pin, which is how we're going to send information to it, is pin number 5. The next part we're going to do here is create an object to interact with the display. As the code that is in the library is object oriented, that is what we're doing here. So we are calling on the TM1637 display library and creating an object called the lander underscore display. Anytime we want to interact with the physical display we hooked into the board, we're going to call on this particular object. And then from here, we just then tell it which 2 pins are which, the clock pin and the DIO pin. All right, let's see here what our notes say. The TM1637 library takes an array of 4 bytes to represent each of the 4 display digits. Within each byte, bit 0 is segment A, and bit 1 is segment B, and so on. The 0 indicates the segment is off, and 1 bit indicates that the segment is on. To show the individual bits in each byte, we will use binary number notation consisting of a 0B followed by 8 bits that can either be a 0 or a 1. For example, 0B, 01, 01, 01, 01. So that's the way that the notation is going to look to us here. We're then going to create an array that turns on all the segments, which is actually really great because that allows us to make sure that the entire 7 segment display actually functions. Could you imagine if you had one of these and one of the segments was burnt out? I think you might lose your mind trying to figure out why your code doesn't work, when in reality, your display doesn't function. It's always good to have in the beginning of your code something that turns everything on ever so briefly to make sure that it all still functions. Or even if not on startup, if you actually have some button or key combination that you program in your code that will then temporarily or briefly turn on everything so you can confirm all of the physical components in the physical world still function. Ironically, the sensor that controls my hand tracking died. I tried many things to try to revive it. I reinstalled drivers. And interestingly enough, I was able to verify that the sensor had died because it mounts as a webcam. The webcam tracks my hands, and then it applies tracking points to that, which then allows me to move my VTuber hands. Something similar you would want to do with your 7-segment display. If you don't turn them all on and confirm that it's working, then you wouldn't know. I knew that my tracker had stopped functioning because I went in and I looked at the camera, and the camera itself no longer displays a picture. If it can't display a picture, there's no way it can capture the tracking points on my hands. So that actually allowed me to confirm that the sensor was bad. That means there's no amount of troubleshooting, reinstalling that I could do that would make the sensor function because it was faulty. Same thing goes for hardware that you plug into your Arduino. If you have a bad component, there's no amount of troubleshooting or code rewriting you can do that would fix that without checking the physical components to make sure that they work. Which is why I'm happy to see that they actually have this function that's called all on that will turn on all of our segments. That allows us to confirm that the thing works. Okay, so it says a 7-segment display is shaped like an 8. It has 7 segments, A through G are the letters, that can be lit up. The diagram below shows the placement of each of the segments. Interesting. Oh, okay, so this is actually showing to you all where they are. So to the top of that 7-segment display is A, which is the first position, and then we go around kind of in a circle. B, C, D, E, F, G is in the center. That one's last. That's very important to know, because some of you might have thought A, B, C, D, but that's not right. It's A, B, C, D, E, F, G's in the center. You come back to it. So that's actually really good to have too, as a nice visual example on what's happening here. Which actually, I'm actually going to copy those comments and bring them over, because I really like that. That's not a bad thing to have over here. And just as a friendly reminder, anything that's in the comments here is not actually compiled by the encoder. It just ignores it, so that you can have as many comments as you want. You don't have to really worry about it, but that does permit you to have at least a decent idea of what you're playing with. Because then future you can look at the code and go, oh yeah, that's what that was for. Let's see here now. It says you can set the individual segments per digit to spell words or create other symbols. The library provides constants for each segment on the display. If you hover your mouse over each of the constants, you can see that each defines a byte with only one bit set to 1. So segment A is equal to the first position being a 1, the rest of them being zeros. In segment B, the first position is a 0, but the second position is B, right? So to turn on A, which is the top segment. Ooh, we're getting a raid. Hello, raiders. Who are we being raided by? We are being raided by Patch Arcana? If I said that right, I apologize if I mispronounced your name. Hello, welcome on in. I am curious. What have you been doing on this lovely platform we call Twitch? Playing a game, doing some art stuff, music, silly things. I'm doing silly things and playing with lights and wires. I said it perfectly right. Excellent. Ooh, okay. A project to build a custom virtual pet. Interesting. Are you doing something with the Arduino suite? Or are you working on some other kind of developmental board? Or is it just like solely, oh, hang on, I'm talking hardware. Is this a virtual pet that solely lives on the computer? Like you would run on your own computer? Or is this like you're building a virtual interactive, kind of like the old, like, chirping dogs from the 90s that you could plug your early onset media player into? What was that thing called? The iDog? I want to say it was the iDog. But then there was also the offshoots of that as well, which is also kind of fun. MSP 430 microcontrollers. Ew, okay. Compete indirectly with the Arduino. It's a basic idea. Oh, that's fair. No, okay, cool. So you are working with another microcontroller suite. Hey, there's nothing wrong with that. This is just so happens to be the kit I picked up. I'm not on any team. If it functions and I can get it to do what I want, hardware's hardware. Good. I'm glad you had fun. Hey, that's totally fair. That's totally fair, Patch. This to me has This has been a learning curve for myself with the 30 Days Lost in Space series. I've always had interest in this kind of stuff, but to actually take it and actually like dive into it, I've dove into shift registers, which you all will be seeing here shortly, sooner or later. Oh yeah, you might have. I normally do the 30 Days in Space thing. If I do it, it's on Wednesdays because I stream on Wednesdays. If it's not that, then I'm usually playing a retro game. But tonight I was in the mood for electronics, so here we are. Tonight we're playing with the 7-segment display that we have right there, chilling out on our workbench. And once we get the code figured out and compiled, we're gonna make it light up and do stuff. So yeah, looking forward to that. Let me see where I'm at here now. Oh yeah, so this makes sense to me. So we have how many positions here? 1, 2, 3, 4, 5, 6, 7, 8 positions before the 0B, which makes sense because if there are 8 segments that we could line up, that means there's 8 numbers that we want to set to a 1 to turn it on. That makes reasonable sense. You're just on is 1, off is 0, and then you just send the whole thing as a nice neat little package that then controls one of those 4 segments. So let's see here. It says the Arduino C++ language uses the pipe symbol operator to do a bitwise OR between values. It takes each corresponding bits in 2 values and the output is 1 if either or both of the corresponding bits is a 1. If both corresponding bits are 0, then the corresponding bit is set to 0. That makes reasonable sense to me. An OR statement requires either the item on the left or the right to be true for the statement itself to be true. Because an AND statement requires both to be true. Otherwise, one condition would be false. If you went to the store and you were told to buy milk or eggs, and you came back just with eggs, well then you did your job and that's true, because you then in fact bought one or the other. If you were told to buy milk and eggs, and you came back with only milk, then it's false. You did not do what you were asked to do, so hence it's false at that point. Bitwise arithmetic is my favorite way to make anything conceptually 5 times harder. Yeah, no, that is fair. I will drink some tea to that. Yeah, I feel that. Off stream, I've been playing with shift registers to control multiple LEDs, and yeah, messing with individual bit shifting is a very much black box magic. I'm here for it, but it hurts my head. I know that that's something that the more I toy with it, the more it'll make sense. At least that's what I tell myself. All right, where's our void here? We're still okay, so we're still above it. Okay, so that's where the loop begins. All right, so the rest of this stuff is still very much above what we have here. So okay, so let's bring this code over. Red Rover. Let Techie bring the code over. Okay. So let's see here. We have our constant byte values, which we have as segment B, C, D, E, G, so on and so forth, to go through them all here. And this actually allows us to spell out the phrase done. So we have a variable called done. And then this is the positions for all 4 segments of our display. So this has to be done in this order for it to spell that word. The D has to be first, then the O, then the N, then the E. And then these segments make that up. So by turning on segment A, D, E, F, and G, is going to print a letter E, right? But if I do these in the wrong order, well, then it won't spell done. This right here on the end is just a comment to remind us what this combination of segments actually is for. Like what it's going to turn out. It's really just for us, just to make sure we know what on earth we're doing. And then let's see here. So we made our object up top called the lander display. So that's what we're doing here. And then interestingly enough, we can actually set the brightness of the display. Interesting. So full brightness is a 7, which looks like that's what we're doing here right out of the gate. We're doing it like an old school cell phone. We're going to turn the brightness all the way up. We're going to turn the volume all the way up. We're going to play the loudest music. You know, we're going to get your attention. We're going full brightness here. I don't know how full brightness is going to look, but we'll see here in a minute. Okay, so that was all done before we go into the logic loop, which means that when we run the compile button, and this uploads to the board, all of this stuff runs once. So we call them both libraries, we then set our pins, we then set a variable called all on, which turns on all the segments. We have our little example to know what letters are where. And then from there, we then have the word done. Now the thing is that these variables were written up top. So the byte variable called done and the byte variable called all underscore on are available to any of the code. I can interact with those in setup. I could put them inside of the loop that runs. I just realized I accidentally copied. I made a boo-boo here. I copied some of the code that... Yep, the set brightness was supposed to go in the setup section. Which means that and that is a rogue, and I meant to move this. This has to go down further. That goes there. Let me just verify that to make sure I didn't accidentally grab an extra brace. Nope, we're good. Get rid of some of this extra white space then that I added. Because then everything else we're going to do, unless there's any of the, unless we write any functions. I don't know if we're doing that this time. I guess we'll see here. Right, that makes sense that we would only set the brightness, at least initially only once. But if we wanted to change the brightness of our display, or maybe we would want to cause what's on the display to change brightness while it's blinking or something to try to get your attention, then I could see us potentially changing the brightness of the display. But initially, for it to be on, I would imagine we need to set some kind of default value, which in this case is, well, 7. And then, let's see here. So, first things first we're going to do is we're going to clear the display at the top of the loop. So that calls the function called clear, which is a built-in function to the library we installed that just turns off all the segments. And then we're going to delay for a full second or 1,000 milliseconds. Then we're going to proceed on. Okay, so then we're going to call the function set segments, and then we're going to pass it which segments we want on. Now we already know that the all underscore on variable that we wrote up top is constant, which means it's not going to change. It's the type byte, but it's going to just be what it is, right? Oh, I have to scroll a little further. It's this one. Indicating all the segments should be turned on. So what we're going to see here is that we're going to just turn them all on, and then delay for a second, and then turn all the segments back off again. So very briefly, we're going to turn on and then flash back off again, which is good. That then verifies that the wiring is correct, at least on the sense of it getting power and ground. And then from there, we're actually going to hop into what we're doing from there. So let's see what kind of example it's giving us. Excuse me. Microwave after a power outage. That's fair. Blinking 12, the show num DECEX function has an additional parameter that turns on the colon after the second digit. So if we take a look, let me see here. I've got a pointer laser here somewhere. There we go. If we take a look here, if I, don't zoom all the way out. Let's grab a pen here. We can see here that there is the two dots between these two segments and these two segments. That is actually controllable. Now, what I don't know is if we can control the top dot individually of the bottom one. But that we're going to have to just wait and see. We'll continue our reading here and see what we've come up with. Alright, so it says the show num DECEX function has an additional parameter to turn on the colon after the second digit. This works well for time displays. The second parameter can also be used to control dots between digits if the display has them. In our case, the hero display only has the colon. Dot/colon enable, the argument is a bit mask, which each bit corresponding to a dot between the digits, or colon mark as implemented by each module. And then IE is the example for displays with dots between each digit, like so. Interesting. So to continue the shift of the bit mask, to turn that on for the first. Interesting. So it ends up being the first 3 positions of our 8-position number that will then interact with the dots in these different positions. That says for displays with just a colon, this is true for our hero display, which must mean that we can't control the top and bottom. It's just simply going to be an all or nothing kind of situation. We have to do it with just the second position. Okay, that kind of makes sense because that's similar to this position right here where it would be a dot instead of a colon. But if I can't control the top from the bottom in the colon, then yeah, that makes sense. It would be the same position. For displays with dots and colons, then it's 3 ones in the beginning of the bit shift. I'm not going to lie to you, this is going to be fairly difficult to wander through, I'm sure. The example isn't hard to follow, but yeah, this is it's getting heavy. Alright, let's bring this over and then let's pick this apart. It is getting heavy. Oh mama. And yes, I am saving my work in between the copy and pastes, just out of normal ideology. Alright, so we're going through a loop here. What does our loop do? So we loop through this statement exactly 4 times. So I will be positions 0, 1, 2, and 3. Because 3 is less than 4, but when we would get to a 5th position, which would be number 4. 4 is not less than 4, so we would end up breaking out. So just as another general reminder, loops start at 0, and so do memory addresses. So this will run a total of 4 times. We then do some stuff here. So the liner display is the name of our display object, and then we call on that class shownum DECEX, which is the one, according to the instructions, that does mess with the colon that's between our 4 programmable numbers that we can set. We're gonna do a little reading here. So it says it takes an int leading 0 false. Display a decibel number with dot control. Display the given argument as a decibel number. The dots between the digits or colon can be individually controlled. Interesting. The dots between the digits or colon can be... Oh, well, right, because the colon would be all by itself considered one thing. To which then, if this makes any sense to me, I don't know what this 1200 is for, though. Looking at this just would indicate to turn on... Oh, this is the number we want to turn on. Okay, so this is the 12... Right, because it was the microwave example. Okay, so this is going to turn on digits 1, 2, and then the zeros on our display. And then we'll have that on for half a second, and then clear it, and then delay again. So just like a microwave, we're going to actually blink 12 p.m. 4 times, delaying half a second off, half a second on. Okay, that makes sense to me. We then jump into the show counter, including negative sign for negative numbers. The negative numbers cannot be less than negative 999, since the negative sign is included, uses the leftmost digit of the display. That makes sense. Obviously you can't go outside of the range of what you can display, because that's going to be included in what we can see. Because if we take a look at our display, we can see here that I can fit a 9 there, a 9 there, and a 9 there. And the very far left is where the negative symbol end up showing up, which means I can't use that for another number that's negative. That's as far as I'll be able to go. So then we're going to go through another example here that is in fact going to count and then display the number to the display. So we're going to go for int I is equal to negative 100, while I is less than or equal to 100. We will then display the number I, delay 50 milliseconds, for that whole loop, and then we delay for a whole second between our next example. Now, I could admit I'm a little confused by that, because oh, okay, so it's incrementing there. Okay, so that's, I was gonna say, how are we gonna make it go bigger or smaller? It's on the end of the for loop. So we're counting up from there. So while I is equal to negative 100 and it's less than 100, we then add, which would then make that negative 99, negative 98, so on and so forth, until we get to 100, and then we pause again, and then we go into our next example. Now this one seems like it's pretty straightforward. Oh, did I not copy? Oh, that's what I wanted. Okay. All right, so we then count to 100, we pause, we then clear the display, and then we pause again. And then finally, we will set the lander equal to the done variable. Now this is where things get a little confusing because variables inside of this compiler doesn't have any kind of symbol indicating this is a variable. We declared this up top, right? It's a byte variable by the name of done, right? So we're not directly passing these letters, D-O-N-E. What we're doing is we're passing the object. We're passing this whole thing to that function to tell the display what to set on all 4 of these segments. And it's just passed as one variable, even though it's multiple segments. And that's totally fine. It's capable of doing that because of the way the library is written. The library is able to accept setting these one at a time instead of having to shift each individual bit in our byte variable, because this could get incredibly ugly without having the library available to us. Howdy, Porsche. Welcome on in. And then after we've said done, we delay for a total of 10 seconds and then repeat the demo again. So then the demo then just goes back to the top of the loop where it turns off all the segments, turns them all on, turns them off, flashes just like a microwave 4 times, counts to 100, clears the display, tells us we're done, and then we cycle again. And then it'll just keep doing that. So with that, I'm going to verify that I copied everything correctly, and I have. So I can see here that we're using 6% of our program space. Global variables use 38 bytes, 1% of dynamic memory, leaving 2010 bytes of local variables for a maximum of 2048 bytes worth of space. That's just simply telling us where we stand from the code we've written, which is really handy because if I didn't have something that could easily tell me how much space I'm taking up, that could be problematic if I didn't know. But without further ado, let me switch to the camera, and now we should actually see this in action. We have all the code we need in the libraries. So as long as I brought it all over correctly, we're going to see some action here when I click the go button. Uploading. Okay. We flashed. Oh, there's our microwave. And now we're counting. Count real fast. And we're done. And then after a full 10 seconds, it's going to cycle again. Yep. Flash like a microwave. That did briefly start at negative 100, and since it's capable of showing negative 999, there's totally nothing wrong with it starting at 100. Negative 100, excuse me. I had some hesitations when I was looking at the code, but that I remember now it was negative 999, that it can go higher than that, or technically lower than that because it's negative numbers. And that is our display. So we have a ground, we have our 5 volts, and then we've got the system clock. So if we had other things that required the system clock, we would just combine them on the same pin for the clock. They would all just share the same system clock pin. So that's how everything stays in time. and then we have just one pin that's then telling the display what things it should be displaying based on what we told it in the code. So with that in mind, let me take a look here. That does make up the remainder of the setup for this. So this, to no surprise to me, is a pretty basic example of how to use the display, but it's very powerful because that gives us all the building blocks that we need to be able to display whatever we like on that display. So if we wanted to treat it like a clock, then we could, right? But then we would then need to write the code that allows us to do what? Set the time. What if there's time zones involved? Is there daylight savings involved? Is there not? So if you wanted to use this like a clock, you likely could, but the having the ability to control all those segments of the display gives us a lot of flexibility on what we can show on it, because we have control over all individual little pieces, which is really nice. That excuse me, that gives us a lot of abilities to do, which is funny because my last creative day 15, we went heavy. This looked like it was gonna be a little heavy, but actually not too bad. Not too bad. I'm curious if we have any questions or confusion about any of that. I'm curious to see if any of you have thoughts of any kind towards it. Because, I'm not gonna lie, I actually thought that was gonna be a little bit more involved than it actually was. I am curious to see where we're gonna end up going with that, though, because in this case, they treated it like a basic clock. Now, understand, there is another display that is included with this kit. So this is controlling individual segments, but the other type of display, you have no idea what's going on. Well, Porsche, we wrote some code, and then we're telling the code to control what's on that little display that we have hooked up to our board. So that is the general gist as to what's going on, and that's hooked up to that board that we have so lovingly sitting on our bench. So yeah, fun times. yeah, and that does give us the ability to display on that whatever we want. Which over time, who knows, you know? You can come up with some fun stuff there. So I do look forward to see what other things they're going to have us do with this. But for now, I think that's about it. So I believe I'll be around for next Wednesday. I should be available. I don't know what I'm doing just yet. We might do retro, or we might do more of this. We shall see. But in the meantime, give me a moment. I'm gonna bring us on out of here. We're gonna go raid a bean. Let me see who's on here. Is my music not gonna play? Pretty please. Oh, there it goes. Alright, cool. So we have a set on, who is the fantastic artist who's come up with all of my fun emotes, amongst other things. And with that, let's go say hello, everyone. I thank you all for your time, for swinging on in here and catching a glimpse of another goofy thing to do here on the Arduino board. And I'll see you all next week. Bye-bye for now.